All right, let's do this. The workthrough for class number 3. Diving straight in, z-scores, normal distribution, probability. Okay, starting with z-scores. Mr. Vomit-Bucket's IQ is 103. Convert this IQ to a z-score using mu is 100, sigma is 15. Okay. When you're starting out with normal distributions, draw, sketch, get the distributions on your paper so that you see how much space I have, so that you have an idea of what you're looking at. Okay. What do I know? IQ is normally distributed with a mean of 100, standard deviation of 15. This is the case, this is reality. Okay, then I know that the mean, mu, is 100. And the standard deviation is 15. I'm gonna put that there. I'm gonna put it here. Sigma, standard deviation, is 15. What does that mean? Well, that means that one standard deviation above the mean is an IQ score of mean plus 1 sigma. 100 mean plus 1 sigma is 115. What do I know? I know that approximately 34% of all observations falls between the mean and plus 1 standard deviation. Because it is a symmetrical distribution, likewise, 34% will fall between, 34% of what? Of the population, everyone in the population. Equally, likewise, 34% will fall between the mean and minus 1 standard deviation. This is not difficult math. 100 minus 1 standard deviation is 85. Together, I now know that 34 plus 34% and a couple of decimals, but I'm trying to keep this simple, 68% of participants, of members in the population, I'm thinking in research terms, 68% of the population will have an IQ between 85 and 115. And I can extend this. Approximately 14% of observations falls between plus 1 and plus 2 standard deviations. 14% and a couple of decimals, 13 point something, doesn't really matter, I'm just going to round it. Okay, well, this is plus 1, and this is another plus 1. Together that makes 2 standard deviations, SDS, standard deviations. 100 plus 15, 115 plus 15, 130. So, 14% has an IQ between 150 and 130. And then together, 34 plus 14, called about 48%, right? Has an IQ between 100 and 130. And of course it goes the other way around too. Minus 2 standard deviations, that would be 70. See if you can reproduce that number. Okay, that was just a little bit of theory, just to get that back in our brain again, because this is difficult stuff, right? Now, the fun thing is, what we can do is we can bring this back to a standard normal distribution. And a standard normal distribution requires a tiny bit of math. But the beauty of a standard normal distribution is that it has a known mean and a known standard deviation. It's always the same. If I would be measuring IQ or aggression scores in the population, or how much people speed on average or whatever, every time I would get different numbers here. But the standard normal distribution always has a mean of 0 and always has a standard deviation of 1. 1, 2, 3, minus 1, minus 2, minus 3. And that's very helpful. Now, Mr. Vomit-Bucket's IQ is 103. We need to convert this to a z-score. Well, what do I know about an IQ of 103? Again, plot something. If this is 100 and this is 115, an IQ of 103 is going to be about there. Is that right? 103, something like that. So I already know that if this is a z-score of 0 and this is a z-score of 1, this number is going to be a z-score that's probably going to be pretty close to 0, but bigger than 0, but smaller than 1. If the IQ would have been 97, I would have a line to the left of this 100, and I would know the value would be negative and a little bit below the mean, so under 0. Now let's do this. Let's just do the math here. So a z-score is computed as x minus mu, that's a strange mu divided by sigma. Okay, well, let's make a grocery list. I know that mu, the mean IQ in the population, I'm gonna make this red again because otherwise you may get confused. This is not z-score, this is in the population. The mu is 100 and sigma, the standard deviation, is 15. This is really real, that's how IQ works in many tests, but you're also given this in the question. Okay, then how do I do the math? Well, the math is not that hard. I take my observation, which is Mr. Vomit Bucket, 103. I subtract the mean, well that's 100, the mean in the population, and I divide by the standard deviation in the population, well that's 15. Okay, it looks to me like I get 3/15 here. Okay, and that means that I can actually simplify this to 1/5. And 1/5, as you may know, is 0.2. Now if you don't know that from the top of your head, that's fine too. Just put 3 divided by 15 in your calculator and I guarantee you're going to find 0.2. Well, what did I say? Did we not expect a z-score a little bit bigger than 0 but quite a bit smaller than 1? Pow! We can do this. Okay, so that's his z-score. Now the next question is question 2. How many standard deviations is Mr. Vomit Bucket's IQ removed from the population mean? 0.2. A z-score expresses the position of a raw data score in a standard normal distribution. And it says how many standard deviation units that score is removed from the mean. 0.2, a fifth of a standard deviation. This would be 1 standard deviation. Now what if you don't believe me? What if you say, that makes no sense to me? Okay, let me prove it to you. It's very simple. Imagine that you would have an IQ of 115. You agree with me? That is 1 standard deviation above the mean, right? 115. 100 plus 15. Okay, minus the population mean divided by the population standard deviation is 15 divided by 15 is 1. This one. Done. Your IQ is 1 standard deviation exactly above the mean. Make sense? If not, let me know. Okay. Question 3. What percentage of people in the population have an IQ higher than Mr. Vomit Bucket's? Okay, well, what am I looking at? I'm just going to do this in blue just because I already marked some stuff there. This is his IQ. Okay, we know this equals a z-score of 0.2. And now I want to know, this is the population. How many people have an IQ higher than his? Well, this line, it's not a very straight line, but you get the point. Anything to the right of this line would be a higher IQ than him. But anything to the left of this line, that would be a lower IQ. But I'm not interested in that right now. I want to see this AUC, area under the curve. Well, to figure that out, you need calculus. But fortunately, all that calculus has been done for us by statisticians. So we have a textbook. We open it to the table in the back. Papers are falling out of my book, that's okay. Appendix A, proportions under the standard normal curve. And what do I see? I see 3 columns, A, B, C. The column on the left is z-scores, then area between mean and z, and then area at or above z. Well, it looks to me like I'm looking for an area at or above z. This IQ or higher. Okay, I already know the z-score. Now, I don't find she's laid out this table very clearly because it doesn't, let's put that down, it doesn't run from here to there, continues on the next page. So this ends here. Now I flip the page and I just keep going. Z-score at the top of the page on the left, I see 0.16, 0.17, 0.18, 0.19, 0.20. That's what we had. 0.20. Okay. Now what do I have? Area between mean and z. But the area between mean and z, well, that's not what I'm interested in. That would be this area between mean and your z. I don't care about that. I want the next column, area at or above z. At or above z. And it tells me for 0.20, 0.4207. And this tells me that's the proportion of people, and if you find proportions hard to deal with, multiply them by 100, and then you get 42.07%. 42.07% of people have an IQ equal to or higher than Mr. Von der Bucket. Not too bad, is it? Practice with the table, it'll become easier. Okay, now we're going to get rid of this. Now what do we have? We have question 4. Professor Schadenfreude has an IQ of 150. Convert this to an this IQ to a z-score using the parameters provided. It says I on question, but it should say in question 1. Okay, well, again, we draw because that makes things easier for us. We know that the mean is 100 with a standard deviation of 15. That means that I have 115 there. That would be plus 1 standard deviation. I don't have to look at the left of this distribution because I already know he's above the mean. What's the next value? 130. What's the next value? 145. I just keep adding 1 standard deviation plus 1 standard deviation, 100 plus 15 plus 15 plus 15. And he is even higher than that. He's something here, right? Because his value is 150. So this is going to be a very small proportion of people. Look at that. A very small percentage of people in the whole population have an IQ that high or higher. Okay. Now how do I convert this to a z-score? First, think. What are you expecting to find as a z-score? A number below 0 or above 0? I hope you would say above 0. After all, this is well above the mean, this number. A lot above 0 or not that much? Well, look at how far away this is. Probably quite far removed. But remember, standard deviations in the standard normal distribution have a value of 1. Standard normal distribution has a mean of 0. This would be the standard normal distribution, S and D, mean of 0, standard deviation of 1. 1, 2, 3, 4. Okay, so I'm thinking we're going to find something pretty close to 3. I know it sounds like a lot of work to reason things through this way, but if you do that, you can immediately tell if your answer is in the right ballpark or if you maybe made a mistake. Okay, well in this case it's pretty simple, isn't it? I have 150 minus 100 divided by 15. Okay, well that's going to be 50 divided by 15, and that's going to be 3 1/3. Okay, 3.333333, etc. Is that what I expected to find? Yes, it is. We can do this. Okay, now what percentage of people in the population have an IQ between 100 and that of Professor Schadenfreude? Okay, now ask yourself, what am I looking at? Again, is the question how many people have an IQ this high or higher? Or is the question an IQ between 100 the mean, and his IQ? That's the question. So now I'm looking at this area under the curve. No longer this area. Then I would answer the question, what percentage of people have an IQ this high or higher? But I'm now asking myself, what percentage of people have an IQ between the mean and my observation? Okay, I already have a Z-score, so I take my textbook, I leaf through it, and on page 701, I find a Z-score of 3.33. And it says, area between mean and Z, 0.4996. 0.4996. What does that value represent? That represents this area. So that's his value, right? 0.4996. In other words, this is still more or less visible, I'll put this here, 49.96%, the proportion times 100 of people have an IQ between the mean and this very high observation. Does that make sense? I would certainly hope so. Look at how few people have a higher IQ, and look how almost everyone has an IQ that falls in that range. And therefore I know this looks like a pretty reasonable answer. Okay, we have left 2 questions. And now we leave behind normal distribution for now, but trust me, it'll keep coming back. And we're going to look at dice. Yeah. Okay. What is the probability of rolling an odd number with a normal fair die? Well, a normal fair die has 6 sides. 1, 2, 3, 4, 5, 6. And it's fair, so that means that every side of the die has the same probability of coming face up. Well, that would be a 6th. Sorry, this is not really, put them too close together. Who wants to bet that at some point this whole thing is going to collapse on top of me? Okay, now, what's the question? Reason it through, right? You see what I did. Statistics are a matter of logical thought, step by step. What are my outcome options? 1, 2, 3, 4, 5, 6. What are their probabilities? 1/6 each. Okay. What's the probability of rolling an odd number with a normal fair die? Well, this is an even number. This is an even number. This is an even number. So I have 1, 3, or 5. There aren't any other flavors. But what if I play Dungeons and Dragons and have a 25-sided die? Yeah, I'm not talking about that. I'm talking about a normal fair die. 6 sides. Okay. Well, what am I doing? Probability of odd. That means that I roll 1 or 3 or 5. Or I roll 1 or 3 or 5. And what do we do when we say or? Add or multiply. Or 3/6. 0.5, 50%. So the probability of rolling an odd number with a normal fair die is 0.5. This is a probability, that's a percentage. If you would do this on a test instead of that, I would forgive you, but this is a probability, it's always a proportion between 0 and 1, and this is a percentage. 50%, 50-50. Of course, 1, 3, 5, or 2, 4, 6. 50-50. That makes sense. We can do this. Okay. Now we're going to go to a coin, our last question for today. What's the probability of tossing the following sequence with a fair coin? Heads, heads, tails, tails. I'm going to represent that again, step by step. Heads, heads, tails, tails. What's the probability of tossing heads? 0.5. It's heads or it's tails. There aren't any other flavors unless the coin lands on its side, but that is very unlikely to happen in our world. What's the probability of tossing heads? 0.5. Probability of tossing coins, tossing tails? Sorry. 0.5. Okay. Now, what is my probability of heads, heads, tails, tails? Well, it's going to be something 0.5, 0.5, 0.5, 0.5. But is it adding or multiplication? Well, let's talk this through. I'm tossing heads and then heads and then tails and then tails. I do it in such an exaggerated fashion to really hammer this point home. If you ask yourself the question all the time like that, bring it back to ors or ends, you'll see this is pretty easy. And, well, that's the multiplication rule. 0.5 times 0.5 times 0.5 times 0.5. Half times a half, etc., blah, blah, blah. Then you get a very small number, 0.0625. A half times a half, that's 0.25 times a half is what is it? 0.125 times a half is this. That makes sense. This 2 times is 0.125. You could, yeah, that's right. Okay, so do the math. Okay, that's the probability, and of course you could multiply this by 100. 6.25%. But again, this is the probability, and that's a percentage. And there we go. The OR rule, the end rule. Done. This was it for this week. Well, class. I hope this was useful. Let me know if any questions arise.